6:04 in the evening, June 24th, 2026. Northern Venezuela cracks open. A magnitude 7.2 earthquake, strong enough on its own to level buildings, rips through the coastline. People run into the streets. Glass rains down. Power flickers out across entire neighborhoods. For a few seconds, it's over. People start to breathe again. Then the ground moves again. 39 seconds. That's all the time that passes before a second earthquake tears through almost the exact same stretch of fault. Bigger this time. Magnitude 7.5. Picture it from above. A satellite view of the Venezuelan coast, dark, and then two shock waves rippling outward from nearly the same point, separated by less time than it takes to read this sentence aloud. Scientists have a name for this. They call it a doublet. Two massive earthquakes, almost back to back, on the same fault. It's one of the rarest patterns in seismology. And on June 24th, it didn't just rattle a region. It brought down apartment towers in a capital city of more than 2 million people. By morning, an entire coastal state had been declared a disaster zone. But here's the part that's kept seismologists up at night ever since. Earthquakes this size aren't supposed to arrive in pairs. Something underground made this fault break twice, almost as one. What was it? To find out, we have to go back to the exact second the first crack opened. It's a national holiday. June 24th marks the Battle of Carabobo, the battle that helped win Venezuela its independence in 1821. Streets are quieter than usual. Offices are closed. Families are home instead of at work. Kids inside instead of at school. That detail will matter in about 60 seconds. At 6:04 p.m., deep beneath the state of Yaracuy, a fault line that has been locked and straining for decades finally gives way. A magnitude 7.2 earthquake erupts near the town of Umare, roughly 175 kilometers west of Caracas. The shaking is violent. Streetlights sway. Car alarms scream. In Caracas, people who felt tremors before instinctively start moving toward open ground. They don't make it in time. 39 seconds later, the ground convulses again, only this time it's worse. Magnitude 7.5, shallower, more destructive, landing on a region the first quake had already shaken loose. Now picture Caracas in that instant. Apartment blocks built decades ago on soft river basin soil begin to twist and buckle. Concrete pancakes floor by floor. In the coastal state of La Guaira, entire residential blocks simply collapse. Slabs jutting into the air, rebar exposed, the ordinary contents of people's homes scattered across the rubble in the open air. Sirens start within minutes. Cell towers overload. Multiple states lose power entirely. Then a tsunami alert goes out along the Caribbean coast. And for a long, agonizing stretch, no one knows whether the ocean is coming next. It's later canceled. But that hour of uncertainty is its own kind of disaster. The death toll starts as scattered, unconfirmed reports. Within 2 days, it has passed 1,000. It keeps rising. Eventually more than 1,700 confirmed dead, over 2,150 injured, and thousands more reported missing in communities rescue crews still haven't reached. Officials report dozens of buildings down in Caracas alone. Aragua, Carabobo, Trujillo, Miranda, all damaged. And the ground refuses to settle. More than 430 aftershocks rattle the region in the days that follow, each one sending people who are already sleeping in the streets running again. Help arrives fast from outside the country. The United States pledges $150 million and deploys search and rescue teams. The FIFA World Cup pauses for a moment of silence. But inside Venezuela, even basic information becomes a battle. The country runs one of the most restricted media environments in the world, and in the days after the quake, hundreds of websites stay blocked. Families abroad are left refreshing dead pages, searching for any sign their relatives are alive. 2 earthquakes, 39 seconds, a nation in ruins. And the deeper you look into how this happened, the stranger the story gets. Because to understand it, you have to stop thinking about the ground as something solid at all. Here's something most people never think about. The ground under your feet is not actually still. The Earth's outer shell isn't one solid piece. It's broken into massive slabs of rock called tectonic plates, and they're always moving. Not in a way you'd ever feel day to day, but constantly, in increments measured in millimeters a year. Now, picture Earth from space. Beneath the Caribbean Sea, an entire slab of crust, the Caribbean Plate, is sliding eastward, scraping past the edge of South America like a car squeezing through a gap that's slightly too narrow for it. 2 centimeters a year, about as fast as your fingernails grow. It sounds harmless. It isn't. Multiply that motion across millions of years, and you get an almost unimaginable amount of tension stored in the rock beneath northern Venezuela. Tension with nowhere to go. Because here's the catch. That sideways grinding doesn't happen smoothly. Press 2 rough wooden boards together and slide them sideways, and they don't glide. They catch, stick, catch again, until enough force builds up that they suddenly lurch forward all at once. That sudden lurch in the earth is an earthquake. In northern Venezuela, this grinding happens along a network of faults, most critically the San Sebastian fault system, a long scar running along the country's northern coast. Geologists call this kind of sideways motion strike-slip faulting. It's the same basic mechanism behind California's San Andreas Fault. For decades, sections of this fault sat locked, waiting, accumulating strain no one could see. On June 24th, part of it finally let go. One major rupture along a fault like this is dangerous enough on its own. This time, the Earth didn't stop at one, and what scientists found when they looked closer was something they almost never see. Seismologists studying the data noticed something strange almost immediately. This wasn't supposed to happen twice. Most large earthquakes are followed by a long tail of much smaller aftershocks, dozens, sometimes hundreds, each one weaker than the last. A second earthquake nearly as powerful as the first, arriving within seconds. That's not the usual script. It has a name, a doublet sequence. 2 earthquakes of similar size in close proximity, separated by a strikingly short window of time. It's one of the rarest patterns in earthquake science. So what actually happened underground? The leading explanation is something called stress transfer. When the first rupture tore through its section of fault, it didn't just release energy. It also shoved a wave of pressure into the rock right next to it, like cracking one floor tile and sending a shock wave of stress into the tile beside it. Normally, that neighboring section holds. The stress isn't quite enough to trigger an immediate second rupture. This time, it wasn't enough to hold. Within 39 seconds, the pressure pushed onto the adjacent fault segment was enough to trigger a second, even larger rupture, magnitude 7.5, cascading along essentially the same plate boundary. Not every scientist agrees on exactly how to describe what happened next. Some seismic networks are treating it as 2 distinct earthquakes, 39 seconds apart. Others describe it as one continuous complex rupture lasting nearly 2 minutes, with multiple fault segments breaking in rapid succession. The raw seismic data is still being picked apart in laboratories right now, and the 2 interpretations aren't fully resolved. What everyone agrees on is the underlying mechanism. One section of an already stressed fault gave way, and that failure almost instantly destabilized the section right next to it. It's the geological equivalent of one support beam buckling, and the beam beside it, already strained to its limit, buckling moments later. The unsettling part isn't that this happened once, it's that the same mechanism can repeat anywhere 2 adjacent fault segments are both already close to their breaking point. And in northern Venezuela, the evidence suggests this region has been sitting close to that point for a very long time. This wasn't the first warning. It wasn't even close. 9 months earlier, in September 2025, a smaller doublet struck nearby, a magnitude 6.2 followed by a magnitude 6.3 on the same fault network just west of where the 2026 quakes would happen. It killed at least 1 person and damaged buildings across 2 states. At the time, it barely made international headlines. In hindsight, it reads like a rehearsal. Wind the clock back further, and the warning signs stack up. In 1967, a magnitude 6.6 earthquake struck near Caracas, killing roughly 240 people and collapsing multiple high-rise apartment buildings, a smaller-scale preview of exactly the kind of destruction the city would see again nearly 60 years later. Go back even further, to 1812, and you find a Caracas earthquake that some modern seismologists now believe may also have involved multiple large ruptures happening in close succession. Essentially a doublet more than 2 centuries before instruments existed to confirm it. And further back still, the 1900 San Narciso earthquake, long considered the most powerful in Venezuela's modern history, until June 24th, 2026 broke that record. Here's the number that should give you pause. In the 250 kilometers surrounding this year's epicenter, there have only been 7 earthquakes of magnitude 6 or larger in the past 100 years. That sounds reassuring. A quiet region, but a quiet fault isn't a safe fault. It's a fault that's been quietly storing tension instead of releasing it year after year for generations. There's one more factor that turned a powerful earthquake into a catastrophic one, and it has nothing to do with the fault itself. Caracas sits partly on a deep sedimentary basin, loose, soft ground that amplifies shaking the way a microphone amplifies sound. Buildings on that basin shook longer and harder than structures on solid bedrock just a few kilometers away. Add widespread informal construction, homes and buildings never engineered for modern seismic codes, and you get a city where even a moderate earthquake turns dangerous, let alone a 7.5 magnitude doublet stacked directly on top of a 7.2. A century of seismic history tells one consistent story. This was never a question of if, only when and how many ruptures would arrive together, which leads to the question every geologist along this coastline is now asking. Zoom out far enough, and Venezuela's earthquake stops being a local story. It becomes one chapter in one of the longest-running collisions on the planet. The Caribbean plate is a strange, relatively small piece of Earth's crust, wedged between North America, South America, and the Pacific. For tens of millions of years, it has been sliding eastward, scraping along the northern edge of South America in a slow-motion collision that never actually finishes. That collision doesn't happen along one clean line. It happens through a tangled web of faults stretching across northern Venezuela and the southern Caribbean, what geologists call a transpressional boundary zone, meaning the plates aren't just sliding past each other, they're being squeezed together at the same time. It's one of the more structurally complicated plate boundaries on Earth, and that complexity is exactly why predicting its behavior is so hard. 2 fault systems in particular, the Bocano Fault running through Venezuela's interior and the San Sebastian system along the coast, have been flagged by geologists for years as likely sources of a future major earthquake. These weren't unknown risks. They were known, mapped, watched, and still no one could say when. That's the uncomfortable truth sitting at the center of earthquake science. We can explain why an earthquake happens with real precision: plate motion, accumulated stress, fault rupture. We can map the danger zones with confidence. What we still cannot do anywhere on Earth with any technology that exists today is predict the exact day, hour, or size of the next one. Venezuela's twin earthquake wasn't some new exotic process. It was the same slow-motion collision that's been shaping this coastline for millions of years, expressing itself in one of its rarest and most violent forms: 2 ruptures, almost as one, which leaves one question left to answer. Not what already happened, but what's happening right now, underground, as you watch this. The ground beneath Venezuela has not gone quiet. More than 430 aftershocks have rattled the region since June 24th. The fault network settling, redistributing stress that didn't fully release during the initial ruptures. Most are far smaller than the main shocks, but scientists are clear that some could still produce strong shaking, especially in buildings already cracked and weakened. And that's the real danger right now. Not a new megaquake, a moderate aftershock hitting a structure that's already half standing. Picture the rescue zones in La Guaira, entire residential blocks reduced to fields of broken concrete, crews working in shifts around the clock, racing against a clock that only moves one direction. International teams, including responders from the United States, are working alongside Venezuelan crews in the most basic brutal calculation in disaster response. The longer someone stays trapped, the lower their odds. Damaged power grids, blocked roads, and disrupted communications are slowing everything down, not just rescues, but the basic act of finding out who's safe and who isn't. Scientists are also watching something less visible, but just as important: how this rupture may have shifted stress onto neighboring sections of the same fault system, the same mechanism that may have triggered the second quake just 39 seconds after the first. Here's where it's critical to be precise. No agency monitoring this disaster is predicting another major earthquake. Earthquake prediction, naming a specific time and place in advance, remains beyond what science can currently do anywhere in the world. What seismologists can say is narrower and more honest. This fault system has now produced 2 large, closely spaced rupture sequences in less than a year. That means continuous monitoring, careful aftershock tracking, and updated hazard maps for the entire region aren't optional. They're essential. For the people of Venezuela, what happens next isn't really a question about seismology anymore. It's whether damaged hospitals can keep running, whether displaced families find shelter before the next storm, whether a country already strained by years of economic hardship can absorb a disaster of this size. The Earth has told its part of the story already. What comes next is in human hands. 39 seconds. That's roughly how long it takes to read this paragraph out loud. That's all the time that separated two earthquakes powerful enough to collapse buildings that had stood for decades, displace tens of thousands of people, and force scientists to rethink how fault systems fail. There's a strange kind of humility in standing at the edge of a disaster like this. We can map the plates. We can trace the faults down to the centimeter. We can explain with real scientific confidence exactly why the ground gave way where it did. And still, in the moment it actually happens, there is no warning, no countdown, just an ordinary holiday evening, and then, in less time than it takes to read a headline, a country living through one of the defining catastrophes in its history. Somewhere beneath Venezuela right now, the fault is still settling. Seismometers are still listening, recording tremors too small for anyone to feel. Scientists are still piecing together exactly what happened in those 39 seconds, and what it means for the millions of people who live along that same restless, unfinished boundary between two slowly colliding worlds. The Earth has been writing this story for 40 million years. On June 24th, it turned the page in 39 seconds. We're still learning how to read it in time.